So today we're going to do logarithms.
Okay.
And so
Those usually can be verbalized pretty easily.
yeah. So the first part of it is finding the inverse of each function.
Okay.
So this problem is h of x equals cube root of x minus 3.
And what are we supposed to do with this?
It's the cube root of x.
The cube root of x. Like that?
Yeah.
Okay, and what are we supposed to do? Find the inverse?
Yeah.
So we're actually dealing with inverse functions, not necessarily log functions here. This is not a log function. Although I guess you could make it one. What's the formula for finding the inverse function? How do you do that? In other words, how do you find inverse functions? It's 2 steps, okay? It's actually 3 steps, because instead of h of x, I'm going to say y.
Okay.
That's first step. Make it in terms of x and y. Second step is what?
You switch y and x.
Switch the variables. Third step, you solve for y, and that will be the inverse. When I solve that, I'll have the inverse. So how do I solve that for y?
You would square root everything by 3.
First of all, this -3 is outside the radical sign.
Oh yeah, so you would add 3.
So I'm going to add 3 to begin with. And this is not square root, this is cube root. So how do I get rid of that cube root radical?
You square it by 3.
You don't square it, you cube it.
Or cube it, yeah.
Yeah, and that's the way to talk about it. You're not squaring it, you're cubing it. Okay, so I got x plus 3 cubed equals y.
Yeah.
And
Okay.
that is the inverse. Now, this y is not the same y as that. So what I really want to write over here is not y, but h inverse of x.
Okay.
There's the inverse right there. But usually, you can think of it as switch the variables and solve for y, always. And then whatever you get is the inverse function. So it's really h inverse of x.
Okay.
What else?
Okay, so the next one is g of x equals 1 over x minus 2.
First step?
The minus 2 is not part of the x.
Okay.
Okay, so the first step is to replace g of x with y.
Yeah, I think this is the best way to go. It's the most understandable. You could do it a couple of ways. I could replace g of x, or I could leave it as g of x, and then when I switch the variables, make it the inverse of x. But personally, I prefer this. Let's deal in terms of x and y. Now what?
You would add 2?
Nope. Next step is switch the variables.
Oh yeah,
always.
Switch the variable.
Now you can actually do it in either order. You don't have to actually switch the variables as the next step. You could add 2.
Okay.
But at some point you have to switch the variables, and I'm a big fan of switching them immediately.
Okay.
Now solve that for y, and what you'll have is G inverse of x.
Okay.
So how do I solve that for y?
So you would add 2 to both sides.
Now what? You're solving for y.
You would multiply by y on both sides.
Okay?
And then
solve for y.
you would divide by
Yes.
xy plus 2.
Not xy. Here's what I got. I got y times x plus 2 equals 1. How do I solve that for y?
You would divide by x plus 2.
Yeah. And there's your answer. Now, again, that y is not the same as that y. This y is actually G inverse of x.
Okay.
So I suppose the fourth step is to take your new y and replace it with G inverse of x.
Okay.
There's really 4 steps. Replace the G of x with y, switch the variables, solve for y, and then take your last y and turn it into G inverse of x.
Okay.
Obviously, y can't be equal to 1 over x plus 2 at the same time being equal to that.
Yeah.
So it has to be the inverse function.
Okay.
All right. Keep going. We'll get to a log problem here at some point.
Okay. So for this, I have to, it says using composites determine if the following functions are inverses.
Okay.
And it gives you 2 equations.
Okay.
So the first equation is g of x equals 4 minus 3 over 2x.
Like that?
Yeah.
What's the second equation?
The second equation is f of x equals 1/2 x plus 3 over 2.
Like that?
It's 1/2 x plus 3 over 2. Yeah.
Okay. All right. The rule, first of all, let me test you. Tell me what g of 1 is.
Uh, 5 over 2.
No, it's 4 minus 3 over 2, right?
Yeah.
In other words, is all I do is substitute 1 for x.
Mm-hmm.
Okay. Over here, tell me what f of 2 is.
1 plus 3 over 2.
Which I believe is 5/2.
Mm-hmm.
Okay. When they talk about composite functions, what they mean is what is g of f of x? Written like that.
Okay.
Well, first of all, what is it? In other words, it's the same thing. Let me write it like this. It's the same thing as g of 1/2. And let me draw a line through that because that's not right. 1/2 x plus 3/2. In In other words, is all I do is put in the parentheses what f of x is.
Yeah.
Now, what's that equal to based on the g of x function?
So it would be 4 minus 3 over 2 times 1/2 x plus 3 over 2.
Exactly. Now, if that, in other words, if g of f of x is equal to x, they are inverses of one another.
Okay.
Now, let's figure out what that's equal to. Let's see, we have 4 minus 3 over x plus 3.
Yeah.
Right? Well, is that x or not? That's equal to g of f of x. And incidentally, the rules on inverse functions, g of f of x has to equal x, and f of g of x has to equal x.
Okay.
Okay. Question is, what is this equal to? Is that equal to x? I don't think so. I don't think I can turn that into x. Maybe I can. Hold on. Let me change colors here. So this would be 4 times x plus 3 over x plus 3 minus 3 over x plus 3. You see how I got that?
Yeah.
In other words, this 4 right there is the same as that 4 right there.
Okay. Yeah.
The only thing is I have a common denominator now. So what I really have is 4x plus 12 minus 3 all over x plus 3. Well, 4x plus 12 minus 3 is the same as 4x plus 9.
Yeah.
Now, is 4x plus 9 over x plus 3 equal to x?
No.
No, it isn't. So that immediately tells you they are not inverses of one another. This is inviolate. In other words, g of f of x, right over here, has to be equal to x. Also, f of g of x has to be equal to x. And that's not equal to x.
Okay.
And it has to be equal to exactly x. Not 2x, not 3x, but exactly x. So I would need this numerator. I don't know what it would take to make this whole thing equal to x. I guess it would be 2 times, I don't know. I can't even think about that yet. But that one's not inverses of one another. You got another one like that?
Yeah.
Okay.
Okay, so this one is g of x equals negative 12 minus 2x divided by 3.
Is the whole thing divided by 3 or just the minus 2x?
The whole thing.
Okay.
And then the next equation is f of x equals negative 5 plus 6x, and the whole thing is divided by 5.
All right. So what we're interested in is either this or this. And what we have to do is show that one of those is equal to x. If it is, then one is the inverse of the other.
Okay.
Okay? So let's just try the simplest. What's g of f of x? And the way I want you to do this is start off by substituting f of x in the parentheses.
Okay.
Right?
Okay.
Now continue that.
Okay, so equals -12 minus 2 times -5 plus 6x divided by 5, and the whole thing is divided by 3.
Whole thing's divided by 3. Very good. All right, if I simplify that, do I get x? I bet I do. So here's what we have. Minus 12 plus 10 minus 12x all over 5. That's the numerator. The denominator is divided by 3. Is that going to end up being equal to x? Let's see, we have minus 2 minus 12x in the numerator. Divided by 5 divided by 3 is 15. That's not x.
Mm-hmm.
That means this is not an inverse of that. I'm surprised they started right off giving you two that were not. Usually it's the other way around. Usually they give you some that are inverses, so you can see that it's equal to x.
Mm-hmm.
This is not particularly helpful, giving you functions that are not inverses of one another, because it's all you do is prove that it's not equal to x.
Mm-hmm.
Let me give you one where I know that one is the inverse of the other.
Okay.
I know that those are inverse functions of one another.
Yeah.
And another way to look at inverse functions is an inverse function undoes what the first function did.
Mm-hmm.
In other words, the first function, I'm squaring x. So if I take the square root of x, I undo that.
Yeah.
But the way to really look at it is we want to go through this process. So what's that equal to?
That's equal to
What's that equal?
root x.
In other words,
Root
I substitute root x for f of x.
Mm-hmm.
Now plug that into the g of x function. So what do you get?
Root x squared.
What's that equal to?
X.
That means they're functions.
Mm-hmm.
Excuse me, that means they're inverse functions. And it doesn't matter whether I did g of f of x or whether I did f of g of x. They both have to equal x. Well, f of g of x is f of x squared, right?
Mm-hmm.
Which is the square root of x squared, which is
X.
So both g of f of x is equal to x, and f of g of x is equal to x.
Mm-hmm.
That's actually the official definition. In other words, if your life depended on it and somebody was wanting you to prove that one function was an inverse of the other, I would do both. That has to be x, and that has to be x. If one of them is not x, I guess I can confidently say, well, I'm not sure how confident I am, but I've never seen a problem where one came out to be x and the other didn't.
Okay.
So you're fairly safe in just proving one of them.
Okay.
Okay? You don't have to necessarily do this one down here. That's just, if you're taking a timed test, that's just wasted effort. If this one gives you x, then they are inverses of one another.
Okay.
Okay? What else?
Okay, so for this, I have to simplify each expression.
Okay.
So this problem is 12 to the power of log 12, 144.
Log base 12 of 144.
Yeah.
Okay, that's how you pronounce that. Log
Okay.
base 12 of 144. Much like
Okay.
f of x. That is not f times x. That
Okay.
is something completely different. It's a function whose variable is x. That's what that means.
Okay.
And you got to simplify that, right?
Yep.
All right. One of the things that's useful to learn in logs is this. B to the log base b of x is equal to what?
1.
It's equal to x.
Okay.
In other words, these cancel one another out, and it's equal to whatever that argument is.
Okay.
So in this case, I've got 12 to the log base 12 of 144. What's that equal to?
144.
Yeah. And I could do it a couple of different ways. First of all, let's figure out what that is. What's y equal to? 12 to what power is equal to 144?
2.
Yeah, so I could replace that whole thing with 2. So it's really 12 squared.
Okay.
144. But remember this formula right here. That's going to come in handy.
Okay.
Okay? Doesn't matter what b is. No matter what b is, that's a true statement.
Okay, so this problem is 9 to the power of log base 320.
Log base 3 of 20. 20 is the argument. Okay, we want to know what that is, right?
Simplify it, yeah.
Okay. Notice that 3 is not the same as 9.
Mm-hmm.
But I can write 9 in terms of 3. How do I do it?
Yeah. 3 squared.
So I got 3 squared. There's my 9. I'm taking that all to the log base 3 of 20.
Yeah.
Yeah, let's see. What can I do here? Can I use the property of logs or exponents to simplify this at all? What do I do when I have double exponentiation? What do I do with the exponents?
You can cancel it.
You multiply.
Okay.
Okay? In other words, here, down here, if I have 3 squared plus 3 to the 4th, what do I do to the exponents? Excuse me, multiplied by 3 to the 4th, what do I do to the exponents?
You add them.
So that's 3 to the 6th. If I have 3 to the 7th divided by 3 to the 4th, what do I do to the exponents?
You subtract them.
And finally, if I have exponentiation, in other words, if I have a to the b all to the c, what do I do to the exponents?
You multiply them.
Exactly. In other words, you always do one level less to the exponents than you're doing to the underlying.
Okay.
Notice that when I was multiplying, I added exponents. When I was dividing, I subtracted exponents. And when I am exponentiation or exponentiating, I'm multiplying exponents. So here's a case where I'm exponentiating. I used to call this double exponentiating, but it's really only single exponentiating.
Okay.
But the fact is, you still use one level less, and multiplication is one level less than exponentiation.
Okay.
So I'm going to multiply those exponents. So what I really get is 3 to the 2 log base 3 of 20.
Yeah.
Now, using the other property of logs, what can I do with that leading 2?
You can square log base 3 of 20.
In other words, I can move it up to be the exponent of 20.
Mm-hmm.
So this becomes 3 to the log base 3 of 20 squared.
Mm-hmm.
That becomes 3 to the log base 3 of 400. What's that answer?
400.
That's how you do it. In other words, you got to get those to be the same.
Okay.
Okay? And once you do, then you can basically cancel that, and whatever that is your answer. This was a little tricky because we had to convert 9 into 3 squared, and we had to apply our rules of logs. Then we had to apply our rules of logs again. And then we have to go back to that basic function that the log base b raised, or some number raised to the log base of that number of the arguments equal to the argument.
Okay.
What else?
Okay. So for this, you have to expand the logarithm.
Okay.
So this one is log, and then in parentheses 6 divided by 5 to the 6th power, and that whole thing is to the 6th power.
All right. Use your logs to break this down. What's the first step you want to do?
You want to write it as multiplication or addition?
It's not going to be multiplication. It's going to be subtraction because we're doing division. But we've got that exponent. Let's get rid of that exponent. What can I do with that exponent of 6? Move it down in front.
Okay.
You can always move it down in front, or if it's in front, you can move it to the exponent.
Okay.
So that's equal to 6 log of 6 over 5. Now, how do you break that down?
6 log of 6 plus 6 log of 5.
It's not plus.
Or minus, I mean.
Minus, because we're doing division. Minus goes with division. And there's your answer.
Okay.
And those are all numbers you can get out of your calculator. I don't know if they want you to take it that far or not. Probably not. Believe it or not, that is the most exact answer. If I were to convert that to a decimal number, it would be an approximation. That is an exact number. So is that. You can't get it on your calculator because it goes out to an infinite number of decimal places. It's like getting pi on your calculator. You can't do it. You can get an approximation of it, but it's always an approximation. So we don't usually convert pi to 3.14 or 3.1459. We leave it as pi because it's an exact number. Same thing with logs. Log of 6 is an irrational number, so it's going to have decimals that go on forever, which means if we convert it to a decimal, we got to round it off. Well, we don't want to round stuff off. We want exact answers. If you're flying to Mars, you don't want anything that's rounded off. You might miss the planet. But if you use exact expressions, you'll be fine.
Okay.
What else?
Okay, so this one you still have to expand, and it's log, and that log of x divided by y to the power of 5. The power of 5 is just for the y.
Aha. That matters. Okay. So this time, I can't take that 5 and stick it in front. Because it's only the denominator that's being raised to the 5th power. It's not both of them.
Okay.
So, what do I want to do first here? I'm doing division.
Okay. So you just want to subtract them?
Yeah. In other words, you want to turn it into 2 log statements, not 1. This is compressed. If you want to expand it, you're going to have multiple log statements. What's the first log?
Log of x minus 5 log of y.
Okay, I would actually prefer you do it in 2 steps like this.
Okay.
And now you can take that 5 and move it in front of that. So you get log of x minus 5 log of y. And that's your answer.
Okay.
Okay? So you know the 3 key log rules. You just have to apply them in the right order. That's the name of this game. Whether you're expanding or compressing, doesn't matter. You need those 3 log rules, and you have to apply them in the right order.
Okay.
Okay, what else you got?
Okay, so for this, I have to condense each expression to a single logarithm.
Okay, that means we're going to have multiple log expressions, and we're going to convert it to a single log expression, the opposite of what we've been doing.
Okay, so this one says 6 log base 3 of u plus 6 log base 3 of v.
Now, these log rules that I'm talking about only work if it's the same base.
Okay.
If one of them was log base 3 and the other one was log base 2, I couldn't do anything.
Okay.
You can only condense or expand if it's the same base.
Okay.
Okay. So what's the first thing we're going to do here?
You're going to put as multiplication.
Okay. What's the answer?
That
6 makes things a little complicated. What should I do with those 6's first?
You should put them as
as exponents.
Yeah.
That probably should always be your first step.
Okay.
It wouldn't have to be in this particular case, but it always works like that. Now, compress them into a single log statement.
Okay.
What goes in those parentheses? We are adding the log functions. So what are we going to do with the arguments?
We're going to multiply them.
Okay, so that's u to the 6th times v to the 6th.
Okay.
Which is the same thing as this. Algebraically, same thing. In other words, this becomes u times v to the 6th. And you can either leave it like that, or you can take that 6, bring it down, and have that. Either answer is, I guess, I really don't know. Notice that there is a different way to do this. That's a proper answer. But notice I could also get it by factoring out a 6, right? See what I did?
Mm-hmm.
And then this becomes 6 times the log base 3 of uv.
Mm-hmm.
So that's an answer, same answer, as it should be. Always has to be the same. Otherwise, we've made a mistake.
Okay.
Okay? Which way you do it, I don't care. I kind of prefer the first way. Take all your leading coefficients and make them exponents and then multiply everything.
Okay. Okay, so the next problem is natural log x minus 4 natural log of y.
Come again? Is it plus or times or what?
So it was natural log of x minus 4 natural log of y.
Ah, I didn't write it right. So it's natural log of x minus 4 natural log of y, right?
Yep.
Okay. Natural log is log to the base e. E is
Okay.
equal to 2.71 rounded off. E is another one of those numbers like pi. It goes on forever. So you'd rather use e than 2.71. E is more accurate.
Okay.
But that's what natural log means. Now, why does it have its own symbol? Because e is such a powerful number in mathematics, and when you get to calculus, everything is natural log. Everything. You don't deal with log base anything anymore in calculus. You deal with natural log. It's because so many systems in our universe are controlled by this number e. E is a it's the second most important number in all of math after pi.
Okay.
Okay? Okay, so what's my first step here?
You could factor out natural log.
No, you can't do that. This is not natural log times x. This is more like f of x. This is the natural log of x.
Okay.
So it's not multiplication. I cannot factor out that natural log. What can I do with that leading coefficient?
You can put it as an exponent.
Okay, so first of all, I get this. I'll put parentheses around that just so you're clear. Now what can I do? I am subtracting 2 natural log functions. I want to turn that into 1 natural log function. What is it?
Natural log and then in parentheses x divided by y over 4.
Y to the 4th power.
Yeah.
It's not y over 4.
Okay.
Okay? And that's your compressed answer.
Okay.
And there's nothing I could do with that. That's as good as you can get. There's not even another way I could write it.
Okay.
Okay?
Okay, so for these, you have to solve.
Okay.
So this one is x equals log base 4 of 5.
Write that in exponential format for me. Actually, hold on a second. Their answer is solve it?
Yeah.
That's a number, right? Can you get it in your calculator? What kind of calculator do you have?
A TI-84.
You cannot get it in your calculator. So there is one more formula you got to remember. change of base. That's what this is. If I'm changing base. So what is, in other words, I can't get that in my calculator. Your calculator does not have a log base 4 key. But it does have a log key. So I can figure out what the log of 5 divided by the log of 4 is. That's just two numbers. That's that number divided by that number.
Okay.
Okay, so that would be your answer. Not what I'm showing. Well, actually, this is the perfect answer. But if he wants it as a decimal, do you have any instructions like round it off to the nearest hundredth or anything like that?
No.
Well, then I would say this is the right answer.
Okay.
That's the only exact answer. I can convert it to a decimal, but it's an approximation.
Okay.
But this change of base formula, remember that. It's pretty easy. It's the log of the upper number divided by the log of the lower number.
Okay.
And believe it or not, this is true. It's also this ratio. If you put that into your calculator, you'll get the same exact thing as if you put that into your calculator. It's also true, I can use any base I want. I can use base 17 if I want. In other words, all three of these ratios are the same. Log of b base 10 divided by log of a base 10 is equal to natural log of b divided by natural log of a, and that is the same ratio of log base 17 of b divided by log base 17 of a. I can use any base I want. Those ratios are all the same. And that's useful to know. It's strange that they're all the same, but they are. Okay? But the most exact answer is this one right there. Log of 5 divided by log of 4. Or natural log of 5 divided by natural log of 4. Either one. Because your calculator has those two keys. You have a natural log key and you have a log base 10 key.
Okay, so now so this is graphing exponential functions.
Okay.
So this one is y equals 4 times 2 to the x.
Okay. Let's talk about exponential functions. They all pretty much look like that. In other words, if I told you that, and I even told you that that point right there was 0, 1, that could be 2 to the x, that could be 19 to the x, that could be 3 to the x. I don't know what the base is based on the shape, because the shape is always the same as long as this 2 is a number greater than 1. If that 2 is a number between 0 and 1, then the shape is the inverse of this. Well, not the inverse. The shape would be, in other words, if this number right there is between 0 and 1, then the thing looks more like that. You with me?
Yeah.
Okay. I wish there was an undo. I'll bet that's an undo. Oh, it is. Good thing I discovered that. Okay. So this function is actually 2 to the x. Now, why do all of them go through this point? Because notice that when x is 0, 2 to the 0 is 1. Even if this was 17 to the x, 17 to the 0 power is 1. So just by looking at the shape of the curve, you can't tell what the base is. However, what transformation is happening with that 4 right there? Think of your transformation rules. When you multiply a function by a number, what are you doing to that function? You're vertically stretching it.
Yeah.
Right?
Okay.
So what a vertical stretch means is that every point on the red curve is going to be, or excuse me, every point on my new curve, the blue curve, is going to be 4 times further away from the x-axis than my red curve. My red curve is 2 to the x. So if I want 4 times 2 to the x, first of all, this point right there has got to go up to there. Right? Oops. See why?
Mm-hmm.
This point right here has to go 4 times further away. This point right here has to go 4 times further away. It's off my chart. So let's take this point right there. That's got to go 4 times further away. Now if I connect my blue curve, it looks very similar, and if I continue, it'll eventually get asymptotic with the x-axis.
Mm-hmm.
But it's not the same as the red curve. In fact, it's not even the same shape. Remember, vertical stretches change the shape also.
Mm-hmm.
So the blue curve is the answer to how to graph that.
Okay.
What you start with is graphing that. And then you vertically stretch it by 4.
Okay.
If it was 2 to the x plus 4, then it would be a vertical shift, which does not change the shape of the red curve, just moves everything up by 4.
Okay.
Okay? Let's do another one.
Okay. So this one is y equals 5 times 1/2 to the x.
Okay, now our base is a number less than 1.
Mm-hmm.
And here's where it makes a difference. Instead of looking like the last curve, this curve decays. Like that. In other words, that curve is y equal 1/2 to the x. Notice as x gets bigger, y gets smaller. In other words, as x becomes 2, y is 1/4. If x is 3, y is 1/8.
Mm-hmm.
So I definitely got it pointed in the right direction, right?
Yep.
And this point here is still 0, 1, no matter what the base is, because any number to the 0 power is equal to 1.
Yep.
So I still go through that same point. That's a key point. You always want to be aware that that point, when you have an exponential function, which is defined as having your variable in the exponent,
Mm-hmm.
there's a huge difference between y equal 1/2 to the x power and y equal 1/2 times x. One is an algebraic expression, the other is an exponential expression.
Okay.
What's the 5 going to do to this?
It's gonna shift it vertically 5.
Not shift. Shifts come from adding or subtracting. When you're multiplying or dividing, you are stretching or shrinking.
Okay.
So this is a stretch.
Yeah.
And the only point I really have on here to go on is that one. So all I'm going to do is move that up 5 units. Because I know that this function over here, when x is 0, y is 5. Right?
Yeah.
So I move it up to here. And every point is going to be 5 times further away from the x-axis. So what I end up with is a different shape,
Mm-hmm.
but it still eventually becomes asymptotic with the x-axis. It's just vertically stretched.
Okay.
In other words, let's just talk about that for a moment. if I have a parabola, y equal x squared, and I vertically stretch it, becomes like this. Why? Because every point moves some number further away from the x-axis. And the result, you get a lot of points, connect them, and you end up with a parabola that's skinnier.
Okay.
So the thing you really want to remember isn't whether it gets skinnier or fatter. It's that every point has to be 5 times further away from the x-axis.
Okay.
And then you'll never get it wrong. Okay? If you remember that. Okay? What else?
Okay, so for this one, you have to solve each equation.
Okay.
So it's log 5 of x equals...
Log base 5.
It's not base this time.
Excuse me. My mistake. Log of 5x.
Mm-hmm.
That's why terminology is so important.
Mm-hmm.
Okay?
Equals log, and then in parentheses, 2x plus 9.
Now, if I've got the log of one thing equals the log of another thing, what can I say about those two things?
You can cancel them.
Can't cancel them. They're equal to one another. Think of it as dividing both sides by log, even though that is not at all what's happening.
Okay.
But you can think of it like that.
Yeah.
It's more like saying if I said 2 to the x equals 2 to the y, you can say x equals y. Has to be.
Mm-hmm.
Well, here we have log base 10 of 5x equals log base 10 of 2x plus 9. So that allows me to make this statement. Has to be true.
Okay.
If you solve that, you get 3x equals 9, x equals 3.
Yep.
And if I put x equals 3, then I get the log of 15, which is a number, equals the log of 15.
Okay.
Go ahead. What do you got?
Okay, so this next one is 2 log base 7 and then 1 minus 2r.
Like that? I call this the argument.
Okay.
So if you're looking for terminology to refer to what you're taking the log of, it's called the, I don't know if everybody calls it the argument, but it's helpful to have a name for it.
Mm-hmm.
Is that, did I write it correctly or not?
There's just no parentheses.
Okay. So it's really the log of 1. Hold on. Hey, my goodness. I'll get it right here eventually. Plus r?
It's 2 log base of 7 of 1 minus 2r.
Okay. I wasn't even close, was I? Okay. If I want, my normal first step would be to do that.
Mm-hmm.
So let's do it. What's 1 squared?
1.
Okay. The log of 1, no matter what the base, is what?
Do
you see why? Because 7 to the 0th power is equal to 1.
Oh, okay, yeah.
And same thing if I had 107.
Mm-hmm.
That's equal to 0. Why? Because 107 to the 0 power equals 1.
Okay.
So the log of 1 is always 0, no matter the base.
Okay.
So I don't even have to do that first step here.
Mm-hmm.
I know that this part is 0. 2 times 0 is 0. So the answer is minus 2r.
Yep.
So sometimes you can bypass that step if you want,
Okay.
especially if it's a 1.
Mm-hmm.
What else, Deb?
Okay, this one is natural log of 2 minus natural log, and then in parentheses 3x plus 2 equals 1.
Whoa. Okay. Like that?
Yep.
Okay. So the first thing we want to do is combine this into a single log expression. What would that be?
Okay.
Always. When you're solving log equations, you always want to do that as your first step. Compress. And I'll show you why. You'll see why here in a minute. What is the compression of the left side of this equation? Got
Okay.
subtraction going on. So what am I going to do to the two arguments?
You're going to divide them.
So it's 2 divided by 3x plus 2.
Mm-hmm.
Now, to solve log equations, when you have a single log expression, put it into exponential format.
Okay.
So how do I put that into exponential? That's a skill that you really have to know, is how to go back and forth between log expression and the equivalent exponential expression. What's the base of natural log?
E.
Okay, let's go ahead and write that in there just to help you. Now, turn that into exponential. The way I do it is the following, and it's the easiest way I know of. Take whatever is on the far left, raise it to the power that's on the far right,
Okay.
and it's equal to the argument. As long as the log is on the left side, you can do that. If I had this reversed, and if I had 1 equals natural log of this, I couldn't do that. But as long as the log is on the left side, it's really easy to convert it. And notice there's only one variable there. That's a number. E is 2.71. So you end up with 3x plus 2 equals 2 divided by E. So 3x equals 2 divided by E minus 2. X equals 2 over E minus 2, all divided by 3. And I could simplify that a little bit more if I wanted to. I don't know that you need to. That's a number. You can get that. If he wants a decimal number, you can put that right into your calculator and do it. I could simplify it a little bit, but, you know, that's algebra. We don't need to do algebra here. All right. What else? We got 2 minutes. We got time for one because I have a 7 o'clock I got.
Okay, so
Then
the
when
last
is your
one.
final?
What?
When is your final?
So I have one this Friday and then one next Tuesday.
Okay. So you won't be needing an appointment after Tuesday of next week?
Yeah.
Okay. I got a big bridge tournament next week. I'm trying to figure out where I'm going to have free time. And I certainly want to give my students my priority. If you got a final coming up, I'll give you a session before it regardless.
Okay. Okay,
What's the
so
last one we're going to do?
this one is log, and then in parentheses, negative 2a plus 9 equals log, and then in parentheses, 7 minus 4a.
Can I say based on that?
Oh, well, you can divide both sides by log.
That's not really what you're doing, as long as you know that. What you're really doing is equating the arguments.
Okay.
So I can now say this.
Mm-hmm.
Now that's a simple algebraic equation you can solve easily.
Yep.
I think you get 2a equals minus 2, a equals minus 1.
Yep.
Now, there's one last thing you have to do. And that is you got to make sure you're not violating any domains.
Okay.
One thing you cannot do is take the log of negative numbers or 0.
Okay.
So if this made that negative, it's not an answer.
Okay.
No solution. But it doesn't make it negative. Makes it the log of 13, or excuse me, the log of 11 equals the log of 11.
Mm-hmm.
So you're fine with this answer. But a lot of log equations are going to end up being quadratics, and you're going to get two answers, because quadratics always give you two answers.
Mm-hmm.
And one of those answers usually violates the original domain. And you have to go back to what they gave you. Always. Don't, in other words, some of these log rules that we talk about where you condense it, you can't go to row 2 to test it. You got to go to row 1.
Okay.
Because a lot of times it'll pass row 2, but it'll fail the domain test on row 1.
Mm-hmm.
That's just an oddity about logs.
Okay.
And you just have to be aware of that. Okay?
Okay.
Fid, I'm going to let you go. And let's see, do we have another one scheduled yet?
Thursday.
Yeah, okay. I'll talk to you Thursday.
Okay. Thank you.
You're welcome. Bye-bye.